Welcome to qnawire.
Okay, we have problem 744, up and down the hill. A 28-kilogram rock approaches the foot of the hill with a speed of 15 meters per second. This hill slopes upward at a constant angle of 40 degrees below the horizontal. The coefficients of side kinetic friction are given, and we're supposed to use energy conservation to find the maximum height above the foot of the hill reached by the rock. Okay, so I'm going to immediately set up the energy conservation that they suggest. So I have initially only kinetic energy, so that's going to be 1/2 mv squared. Okay, and then I need to subtract the amount of friction that is on the hill. So in order to do that, I'm going to need to find how much friction force acts on the block. And friction force is determined by the coefficient of kinetic friction multiplied by the normal force. And normal force here is going to be equal and opposite to the component of gravity in that direction. So we have this normal force is going to be equal to mg cosine of 40 degrees. Okay, so that means the friction force acting on this block as it travels up the ramp is going to be mu k times mg cosine of 40 degrees. Let's make that look like a G. Okay, so then I need to find the work by multiplying that friction force times the distance it goes up the ramp, and I'm going to label this distance as d. So that's going to be mu k times mass times g times cosine of 40 degrees, then times d. Okay, so then that's going to be equal to the potential energy, which I'm going to write in terms of h, and then as the height above the base of the ramp. So that's going to be mgh. And then what I can do is then I'm going to find a relationship between d and h, and that's pretty straightforward. We have h is equal to hypotenuse times t sine of 40. So we have h equals d sine 40 degrees. And then we can plug that in for d here since we're solving for h. So then I'm going to erase this, if I can figure out how erase works. And I'm going to plug in h over sine 40 degrees. Okay, so then I can do some substitution and simplification. We can get rid of the mass here. This cosine of 40 over sine of 40 is a cotangent, and then you can plug that into your calculator. But what I get overall is I'm going to write 1/2 15 meters per second squared minus 0.2. That's the coefficient of kinetic friction. And then that's going to be times 9.81. I'm leaving off units here just to make it simple for me. 1.192. That's the cotangent of 40 times h. That's a 2, not a z, equals to 9.81 h. Okay, then I get 112.5 meters per second squared minus 2.34, and then these are all the acceleration, so that's going to be meters, that's meters squared per second squared, that's going to be meters per second squared times h was in meter, equal to 9.81 meters per second squared h. Okay, and then that's just adding and dividing. So then we get h is equal to 9.26 meters. So again, that's from the base of the ramp up to the top where it stops is h. Okay, so b is finding will the rock remain at rest at its highest point or slide back down the hill. So in order to do that, let's again make a free body diagram of this block at the angle of 40 degrees that it is at. We have gravity acting on it, the normal force from the block interacting with the slope itself. And then we need to find out whether the gravitational force component that is parallel to the slope is going to be greater or less than the static friction force due to the normal force there. So we have gravity here. So in order to find the component of gravity, that's going to be the sine of this hypotenuse. So then that's just going to be sine of 40 g, and that's going to be our acceleration down the slope due to gravity. And then what we have here is we're going to have the force acting on the block due to the coefficient of static friction times the normal force. So then that's going to be, and that should really be clear here. It's going to be force due to gravity is equal to m times g times sine 40. And then we have the friction force. It's going to be equal to that mu sub s times mg cosine 40 again. That's the normal force. So what we can do then is we can find what sine of 40 is, cosine of 40 is, and u sub s. Because we have mg, we can just leave those units there. So then that's going to be 0.643 mg, and this is going to be 0.57 mg. So we see here that the force due to gravity is larger than the static force due to friction. The force due to static friction. So that means that it is going to go back down the slope. Okay, then from there, it is straightforward to set this up again. So I'm going to go to a new page, and I'm going to write down that we have the initial potential energy when a block is up at the height at the top of the ramp. And then we need to subtract again the amount of work done by friction as the block travels down the slope. So that's going to be u sub k times mg cosine of 40. I'm going to again just substitute in what that distance is. So we have sine of 40 degrees, and then that's equal to 1/2 mv squared. That's the kinetic energy at the base. And since we're trying to find the velocity, we can just cancel out the mass here. Okay, then what we can do is we can write down what our terms are again. So we have gh minus, and since we crossed out mass here, you notice we get the same thing we've had before. So that should simplify back down to 2.34 h equal to 1/2 v squared. And then we can just substitute in what h is and g, and then solve for v. And we get here that v is equal to 11.76 meters per second. And we'll notice that this is less than the velocity that the mass had when it was going up the ramp. So that was 15 meters per second. You know, it goes back up and then back down, and then afterwards it comes back with a lower velocity. And that should be that's due to friction, which is as expected.